We have reasons, usually pretty darn good reasons, for everything that we do and everything we require. Our decisions are based on our charge from NASA to preserve not just the data, but its usability for the benefit of users now and in future generations. And that, plus 30 years in the business, creates a unique archiving perspective that permeates our standards and practices. The answers to most of the little whys are related to the biggest why. Why is there a PDS-4 in the first place? And to explain that, we'll go back to the beginning, and I will give you a, come on, computer, work with me, a very brief history of the planetary data system. It all started around 1980 when NASA realized it was facing a data crisis. Data stored on analog media like film or scan tapes were degrading, as were digital data on magnetic media. What floods weren't erasing quickly, time was eroding slowly. Worse than that, the data was typically delivered from missions first to PIs, they got the data tapes, and the PIs were responsible for cleaning it up, putting it in an analytical format, documenting it, and depositing it with the then NSSDC for permanent storage and public access. This did not happen with the sort of regularity that NASA wanted to see, and the documentation quality varied wildly from PI to PI. Worse still, users were trying to reuse those data even just a few years later, and they were discovering that the documentation, even when it was conscientiously supplied, was not sufficient to actually use the data. So they had a situation where less than 10 years after the last Apollo mission, some of the Apollo data were already considered unusable. NASA was losing the return on its investment in the space program. So the Committee on Data Management and Computing, CODMAC, began meeting to address this for the first time in 1982. And they produced from that meeting the first CODMAC report, known as CODMAC 1. They recommended the creation of data systems, one for planetary, yes, but also a series of other data systems to house the data with researchers who understood it and could curate it to ensure its usability into the indefinite future. A year later, we had the Planetary Data Workshop, which was convened at Goddard Space Flight Center, to work out the details. And two separate projects emerged from that program, from that workshop. There was the pilot planetary data system on the one hand, and the planetary data system on the other. They were started by two different codes at Goddard, and they proceeded in parallel for a while. In 1985, those two efforts were merged into a single effort that kept the planetary data system title. And in 1986, the project formally reviewed the system requirements document that would define the new planetary data system. It is important to note that from the very first CODMAC report and on through all of the subsequent meeting, workshopping, and designing, the imperative was and still is to preserve both the data and its usability for future generations. So let's take a moment to consider the state of information technology in 1986. First, any significant quantity of digital data that needs to go someplace is shipped on magnetic tape, with only a very few localized exceptions. That's because there is no internet, not as we know it today. There are some networks of cooperating institutions. They're called things like SPAN, BitNet, and of course, the famous ARPANET. And there is some file sharing going on within the individual networks. Some networks are connected by gateways that pass traffic from one network to another, but TCP/IP, although it exists, is not widely implemented yet. The NASA Science Internet is still 2 years away. There is email, but no attachments, and you have to know how to route it yourself through the right sequence of network gateways to get it to your recipient if he's not on your own network. The IEEE 754 floating point standard is only a year old and is very far from universally implemented. And a CERN employee named Tim Berners-Lee was still 3 years away from naming his personal hypertext project the World Wide Web. So in that environment, the PDS system requirements document laid down an ambitious design for preserving, cataloging, and distributing planetary datasets to users over technology that really wasn't quite there yet. The plan presented in the review called for a 3-stage rollout. PDS version 1, the first release, was focused on software infrastructure and designing the catalog that users would use to interface to the data. PDS version 2 would start basic operations in the central cataloging and distribution node, with 2 selected discipline nodes being brought up to full operational status as test cases, and they had detailed catalogs at the nodes to serve the data sets that they held themselves to a greater level than the general catalog. And then finally, PDS version 3 would be the final release with all discipline nodes fully operational and all user support in place. In the final presentation of that successful review, project manager Tom Renfro produced a list of issues and concerns, the very first of which was: the current scope of the complete statement of the functional capability for version 1 does not match the resources available, which is an interesting precursor. And I'll add this quote from a subsequent page for my PDS colleagues. And remember, this is 1986, 4 years before there actually is a PDS. Node personnel are already overextended. How, you may ask, could PDS be underfunded and overextended 4 years before it was even a thing? Well, there's a pretty good reason for that. Archiving is not just file storage. Okay, nobody really thought it was just file storage. But when you sit down to work out all of the details of how users will find data, how the system will track data in the holdings, how you will copy and dispatch it, how you're going to make sure the archival copies are refreshed so they don't degrade, how you go about defining and collecting the information you need to describe the data to the users, how you demonstrate usability, and so on and so on. It is a lot more work than even the people who knew it was going to be a lot of work thought it would be. By the way, as you might suspect, the version identifier PDS3 is loosely tied to this original schedule, but only very loosely. So here's what happened after the requirements review. In 1990, PDS version 1 was, in fact, declared operational. It goes live with all discipline nodes starting work at once. There was a delivery review for this release in 1989. Interestingly, the list of system documentation presented in that review did not include a standards document or user preparation guide. We'll get to why in a little while. There was another major milestone in 1992. SVN hires me, yay! The version 2 and version 3 designations were dropped right around the time of that version 1 delivery review because the original rollout plan did not survive the very rapid evolution of the internet and related technologies or the massive inherent difficulty of the task. References to version 2 and 3 are in the past tense in that document. They talk about requirements that were intended for version 2 and rescheduling them, but future implementations are referred to as PDS 93 or PDS 96. So in the 1992 to 93 timeframe, we have what was known mainly retrospectively as PDS 2. The first standards document was finally produced during this period, and the Planetary Science Data Dictionary, the PSDD, is created to define all the keywords that will be used in all PDS labels, with the intention that that set of keywords, that dictionary, could also be used by other projects so that planetary science would have a common vocabulary. And PDS follows fairly closely on its, PDS3 rather, follows fairly closely on the heels of that era as a result of an overhaul of the standards in response to, let's call it, feedback from users and data preparers. Two major changes happened between the PDS2 era and PDS3. First, major simplifications were made to some of the catalog file structures. For those of you who aren't familiar with PDS3 structure, the catalog files were literally used to load a catalog database that users were expected to search to locate and order data sets. The initial design of things like the instrument file, however, had dozens of extremely specific fields, including things like serial numbers for the hardware, that had no application to the sorts of searches that end users actually wanted to do to find data. And then on top of that, they required knowledge that archiving team members had no access to. So they were very specifically defined for the instruments, the first few instruments that were used as prototypes for the PDS. And so they had almost no reusability. And if it was not an imaging instrument, as the first prototype archives were for, then the catalog file contained large stretches of not applicable, just row after row of things that couldn't be filled in. So these massive catalog files were streamlined to include just a few searchable keywords, high-level concepts, and then human-readable descriptions. The second major change was an attempt to rationalize and standardize the keywords used in labels. More specifically, some minimal metadata requirements were imposed where there weren't any prior to this point. This, of course, presented a non-backwards compatible change in the standards, so a new version number was in order, some way to let programmers know this is the new version of the label and you can expect to find certain things. And so the standards were updated, and this new version with its new metadata requirements was identified as PDS3 to distinguish it from the previous version. But you will never see PDS2 in a label as a version identifier. PDS3 was the first time that that concept was introduced to the labels. So the key characteristics now of this PDS3 standard, which was used for the next 15 to 20 years. Happily, CD-ROM replaced magnetic media as the hard media storage format and distribution format for PDS datasets. The assumption that data would always be distributed in units no smaller than a complete volume permeates the PDS3 standards. You see chapters on it, you see references to it. The data structures, the directory structures rather, are set up all on the assumption that you're talking about a single volume. Formal information modeling was applied to derive the catalog file metadata structures, the original ones and the streamlined ones. These structures were rigidly controlled, and after the major change from PDS2 to PDS3, streamlining that process, they remained unchanged with very rare exceptions, maybe 3 times that I can think of right offhand, over the next 15 years. So the formal modeling approach made for a very stable system of cataloging information, and in that respect was really a great success. On the other hand, the approach applied to data structures and product labels, I will graciously describe as informal modeling. The process actually went like this. The first time a data structure was encountered for archiving, the first image, the first character table, and so on, it became an archetype. The initial collection of archetypes from PDS1 development became the data structures included in the first standards document that was written for PDS2 after a number of missions, legacy missions, had their data sets archived. From that point forward, when a new file format came in with a different data structure, which happened regularly as instruments became more sophisticated in what they could do and how they could optimize DSN bandwidth, the data engineers would determine what alterations and additions were needed to the standards to enable the new data structure to be considered compliant. Really. Finally, anything that wasn't observational data, like all that precious documentation, your ancillary files, your calibration files, filter curves, things like that, none of that was cataloged and tracked as part of the system. If the document you wanted wasn't on the volume in your hands, there was no easy way to find it, or even to determine if it existed in the archive in the first place. So, in hindsight, knowing how information technology evolved through the 90s and the early 2000s, the situation inside the archive was precarious from the start. Outside the archive, PDS as an organization had some major obstacles to deal with as well. First, and it is important to realize this, PDS had and really has no enforcement authority. All we can do is report to NASA that you failed to meet your archiving requirement. And for many years, doing so elicited no response from NASA headquarters. And because archiving was the last act of a mission, raiding archiving funds to deal with cost overruns was commonplace. It took a while, but NASA got increasingly aggressive about ensuring that archiving happened till we reached the point where we are today, where archiving is a clear requirement. even for Rose's proposers who are not proposing major missions, but just to create new data sets and analyze data sets. Data analysis programs have archiving requirements. The earliest missions that were required to archive with PDS were designed and budgeted before there was a PDS. This includes the Cassini mission, which launched in 1997 and had to do PDS archiving with their original data management budget and with no comparable precedents in the PDS. No mission of that size was in the PDS to act as a guide for them. Every mission that finally sat down to attempt to archive data with PDS learned the same surprisingly hard lesson that the 1986 Requirements Review Panel learned: archiving is not a trivial activity. This still happens now, actually. I have yet to hear of anyone ever overestimating how much work it would be to create a planetary archive, but we're trying one day. Data preparers were either frustrated by standards that were not prescriptive enough to code their pipelines to, or they expected it to be relatively easy to get their pipeline output format accepted as archival and added to the standards because of other groups having already achieved that distinction. The first PDS end users, who had been anxiously awaiting these new, well-documented, usable data sets, were not at all happy with the results of data engineering approach taken with the data products and their labels. When end users had to modify code to deal with a change introduced in a previously existing data structure, they viewed that as a new format. The fact that the new format had the same name as the old format did not help. And more PDS was hearing calls for fewer, simpler formats and better usability. This did not have the effect you might expect. Why? Well, fewer, simpler formats and better usability had to be interpreted in some context. When they were interpreted by the data engineers, this is what we got. Keyword proliferation is a bad thing. Proliferation was determined by the total number of keywords in the Planetary Science Data Dictionary. The reasonable idea was that missions should not redefine common concepts every time they were used. So when a concept was proposed for a label, if there was a similar keyword already in the PSDD, it must be used. But frequently there were context-dependent nuances of meaning. So the definition of the keyword was modified, usually with caveats about interpretation in the specific context in the human readable format, sometimes the extrema, not data types. You couldn't break things that were readable in the PDS, of course. Format proliferation is a bad thing. Proliferation here was determined by counting the number of values on the right-hand side of the object equals statement that were used to define data structures in PDS-3 labels. As new data structures came in, if they almost fit something already defined, then the existing definition was modified to accommodate the new data structure. Community standard formats are a good thing. Community standard formats are essentially formats produced by software that has a large, cohesive user base. Certainly, these formats are usable to the software communities that wanted them, and so completely new data structures were added to the standards for formats that were successfully argued to be community standards. These formats were effectively software dependent, and it included things like compressed formats, interleaved data structures, and things like that. As a result of these interpretations, what end users perceived as the response to their calls for fewer, simpler formats was more complexity in the application of the standards, more uncertainty about how the standards should be interpreted in any specific context, more ways of arranging bytes in a file, and more demands for more of the same from the data preparers who were working with limited resources. In fact, the entire PDS-3 approach to archiving could be summed up as modify the standards to fit the data. And there were consequences. On the end user side, modifications to keyword definitions undermined confidence in the PSDD. It was clear to everyone that definitions were being modified as time went on. If you were looking up the definition of a keyword you found in a Voyager label and it referred to Cassini, you knew that something had changed. But it was not possible for a user to determine what the definition of a keyword was at the time that any particular data set was archived. Neither was there a way to verify that any nuance mentioned in the definition either was or wasn't applicable to any other context that might have been mentioned or not. Simple basic data structures like tables and images developed ad hoc complexity like structured subfields and interleaving with other data structures in the same data file. So many accommodations had been made for the quirks of specific pipeline products that it was effectively impossible to write code even to support basic I/O on everything labeled as an image object, let alone support any sort of generalized processing or analysis. Documentation became critical to the survival of the data. With no formal requirements for label metadata beyond the bare minimum and the issues with keyword definitions and structure description, documentation was essential to fill in the increasing number of cracks in the system for users who wanted to use the data. There was a long-held belief that any sufficiently well-documented data set is usable. But documentation was rarely that sufficient. And as technology evolved, undocumented assumptions about what everybody knows were routinely invalidated, which only added to the confusion. Meanwhile, inside PDS, more design work was needed for each new instrument or experiment that needed to archive data. Fortunately, more and more planetary missions were being selected and funded. That was a great thing. But the increasing effort inside PDS came from having to re-engineer existing keywords and data structures for all these new data sources in ways that would not break existing data sets. Uncertainty about what was in any particular label in the legacy data maximized the probability that this would fail with increasing frequency. Supporting even basic display access to data was all but impossible. There were differences in structural details, undocumented default values, and tacit assumptions about things like storage order and display order riddling the legacy archive. Coding the logic and contingencies needed to handle even just all image data was already intractable. Users were increasingly demanding online access to data products, which overall is a good thing. It's certainly cheaper than mailing disks around. But inconsistent metadata and product labels from different sources, let alone different eras of the PDS, made it virtually impossible to create generic interfaces that could support either automatic or at least low effort extension to new datasets. In more than a few cases, PDS discipline nodes had to produce additional metadata or resolve discrepancies in archive metadata in order to provide the product level search and selection capabilities users needed and expected to have. Users also wanted data products that could be fed directly into processing software. No vendor could support PDS3 format for all the reasons we've already mentioned. So frustrated users and beleaguered data providers turned to demanding that software-dependent formats be accepted as archival formats because they were at least usable. But software-dependent formats are no more durable than the software that produces them. So adding them to the archive meant that PDS now had to budget for format migration as well as medium migration in order to maintain the usability of those archival data after their software environment no longer existed. And this brings us up to about 2005. At this point, the oldest data sets in the node archives, written to CD media in the early to mid-90s, were reaching the point where it was time to plan for refreshing the archive. After 15 years of data collection, PDS needed to worry about media migration. And then there was the DVD debacle. I'll get to that in a minute. So PDS had increasingly unsupportable standards, hard media reaching the end of its reliable shelf life, and more formats in its holdings than it could literally count. Because if the metadata was sketchy enough, you couldn't be sure if formats from two different sources really were identical or just looked that way from the metadata you could see in the labels. And that brought us to the breaking point. Yes, there were red flags all over the place, but the whistle of the incoming bomb that we started hearing was a nightmare scenario for PDS: data loss. PDS exists to ensure that data survives and remains usable. We review data when it comes into the archive to prove it is usable when we get it. If the data is lost after that, either physically or logically, PDS has failed in its primary task. And when an archive fails, it fails this generation and all the generations that follow. Because of the accumulation of problems resulting from the make the standards fit the data approach, in the early 2000s, PDS had to rescue data from its own archives. And I'll give you 3 quick examples. The International Halley Watch, Near Nucleus Studies Network, and Large Scale Phenomena Network. They were image collections. They were stored as compressed data. The IHW data collection was the first major data collection that SBN archived. It was the first thing I worked on when I was hired. These 2 networks produced what was considered at the time to be a huge amount of data. It was, in fact, about 25 gigabytes, all told. The archive was to be published as a set of CD-ROMs. Now remember, this is in 1992, and this was still a commercial CD-ROM production process. So we created a master file, it was sent off to a factory, a glass master was made, and you had to run off at least 300 of the things, which were then distributed by mail and sent to the NSSDC for safekeeping. So in order to avoid breaking the production and shipping budgets, the image data were written to CD in compressed format, which got them down onto 19 of the 24 CD-ROMs in the set. The compression algorithm used was public domain, which was important at the time because there were still trademark and patent infringement lawsuits working their way through the courts on various compression algorithms, including the one that I believe was underneath the PK-zip package, which was around at the time. Fortran and C source code and executables were included on the disks for future generations because we didn't seriously believe that the code, the executables, would work for any length of time. By the time the CDs were mastered and distributed, the executables didn't run on most systems. By the time SBN was looking to refresh the media, neither version of the source code would compile either. The source code was sparsely commented. The algorithm, as it turned out, was not sufficiently well documented. We gave a student, a comp sci student, the task of working on that project for the better part of a year to decrypt the compressed data using the source code, the minimal documentation, and a truly impressive amount of trial and error. Ultimately, the student was successful and consequently much more employable. Second case, also a small bodies node case, the near-Earth asteroid rendezvous data. And this was a direct result of the DVD debacle. The NEAR mission encountered arose and ended in 2001. Writing the mission archive would have required several hundred CDs for each copy, CDs that we were now creating locally rather than mastering. But even still, it would have taken more than half of a full-time employee's year to record and verify the nearly 1,000 CDs needed for the 3 physical backups we were required to have. Our service copy that users used, our local backup copy, and of course the copy that we sent to our deep archive at the NSSDC. Happily, we thought, DVD-R came along at just the right time to solve the what are we going to do about all these CDs problem. So we got our DVD-R readers and writers, and the mission archive, all 3 copies, was written to DVD-R. We mounted the service copy in our jukebox and carried on with our business. A year or so later, users started reporting I/O errors trying to read the NEAR data from our service copy. We investigated and found many I/O errors ourselves surfacing on these disks, and it turned out we were not the only ones making similar discoveries on relatively new DVDs produced to hold data. At this point, PPI Node led an investigation into the DVD-R media. The conclusion was that DVD-R was not a feasible archive medium for PDS. It was designed for sound and video. If you drop a byte here or there in a movie or soundtrack, no one notices. Well, maybe one guy notices. But if PDS loses even 1 byte of data from an archive, we failed. DVD-R was unreliable even at initial write time, It was not uncommon for an immediate checksum after writing the disk to fail 30 to 50% of the time. And from some manufacturers, the failure rate was over 90%. And it clearly did not have an archival shelf life. Well, spinning disk was the only viable alternative, but it was at least within our budget. So we immediately sat down with our copies of the disks and transferred the near data from DVD to spinning disk. Many of those DVDs failed. And for one volume, all 3 copies, our service copy, our local backup, and the copy at the NSSDC, all failed with read errors. We did finally manage to recover those data by walking that one disk around to all 5 DVD readers we had at the time at various temperatures, and did finally, after a couple weeks of effort, manage to save the data. But it was a very near thing. And the last example I will give you is from Cassini, specifically the CIRS and VIMS data. And this is a case of software-dependent formats. Now remember, Cassini was budgeted before PDS existed, and its pipelines were developed during that PDS2 to PDS3 transitional era. These 2 instruments produced data products using software that had an existing user community. Also, thanks to the usability argument, these data were accepted in those formats for archive. In the case of CIRS, the software was vanilla, a package developed for the Mars Global Surveyor mission test instrument. And that team had already successfully argued that the software format should be considered archivable. The format amounted to what was described in the 1980s as heap storage. It was an unstructured block of bytes with a lookup table that contained rows of data type information and pointers into the heap where each variable length record began. The PDS3 format for these data was a table object for the lookup table and a file described simply as file for the heap. No PDS tools supported, or indeed, I'm sorry, I've actually gone backwards. Here we go. No PDS tools supported this format then or now, even for simple basic I/O. The archive volumes did include source code for vanilla, as well as a now 20-year-old preliminary draft of a user's guide. The VIMS data were archived in the format produced by the USGS-developed ISIS-2 software. And ISIS is still around. It's now at version 3. So this is a relatively large, fairly stable user community. So the ISIS-2 format was added to the PDS standards as the cube with a Q object, but non-ISIS users found this format difficult, if not impossible, to read because planes of the core cube, lines of the back planes, and rows of the side planes were all interleaved with each other. And unless you were a serious programmer with professional aspirations, disentangling that kind of format was extremely difficult to do just based on the documentation that was available in PDS. In both cases, these software formats incorporated into the standards in the name of usability had the opposite effect of making the data unusable outside of their specific software environments. Now, the Ring Moon system node has expended significant FTEs doing format migration of these data into software independent forms for the broader interdisciplinary community, and they're the ones who sent me these lovely little press images on this slide here. As PDS was dealing internally with worries like these, the outside world, annoyingly enough, refused to stand still. We did catch a break every once in a while, though, to be fair. Preservation, for example. The approach to preservation evolved from creating and refreshing physical media, a very labor-intensive and expensive task, to integrity checking of multiple copies maintained on spinning disk. So media migration is not a major frontline activity of the PDS anymore. Hand in hand with this, data distribution moved very rapidly away from mailing disks to downloading entire data sets to downloading just selected files. This is way cheaper than mailing bits around the countryside. On the not so upside, among end users, the threshold for usability also evolved. So it started with, I could write a program to read this around 1990, and that moved on to, I have a converter that will read this, which worked for a little while around 1995, to, I want to feed this directly into my preferred analysis package, around 2000. And right now it is heading full steam toward, I want to process the data in the cloud and just get the result. Thank you very much. And as we shall discuss shortly, this was highly problematic for the PDS-3 archive. So we're up to about 2008. And push comes to shove. A second attempt is made at retro-modeling, that is, retrofitting a formal, consistent information model onto the structures in the PDS-3 standards. The conclusion of this analysis was that you could not do that without invalidating at least some of the formats in the legacy data, and so implementing that model would require substantial format migration of legacy data. Even then, it was not at all clear that that would eliminate all the logical issues known and unknown to be lurking in those product labels, particularly with respect to missing metadata or undocumented assumptions. Clearly, the PDS-3 data structures were not tenable long-term. Because of the large amount of uncertainty in data structure description from context to context, the effort needed to develop tools to work across seemingly similar data types, but from different sources, scaled with the number of data sources. Even PDS struggled to provide tools to work across missions. Third-party developers, not surprisingly, never appeared. End users increasingly wanted to cherry-pick products within and across datasets and data sources, rather than downloading entire datasets to their own disk space. Recall that at PDS-3, at its core, was not designed for that. It was designed for volume distribution. The ad hoc approach to product-level metadata outside of data structures provided little basis for discoverability below the dataset label and no basis for common analysis across data sources. You just didn't know from one source to another what keywords you would find in the label and what would be in documentation and separate files and things like that. The prospect of going through the legacy product labels keyword by keyword, even to assess the full extent of the metadata problems in the data labels, gave the stoutest hearts fainting spells. So we couldn't stick with what we had, and we couldn't see a tractable way to fix it and move forward. So those of us analyzing the problems began vigorously suggesting it was time for a redesign. It was a majority decision. There were some dissenters, but it was a decision nonetheless. So why PDS-4? Well, 3 reasons. If we were going to have to do format migration anyway, we only wanted to do it once. We were fast approaching the point where we needed to seek out data formats already in the archive that were becoming unreadable, like the compressed Halley watch images and like the vanilla-based format, because vanilla has not, to my knowledge, caught on as a substantial user community. We needed to start worrying about that data being lost. If we were going to have to do format migration anyway to get a stable standard system, we only wanted to do it once and then never again if we could possibly avoid it. Second, to create a design that would serve the needs of data preparers, end users, and PDS as curator of the system equally and all at the same time would require expertise in all aspects of planetary data collection and analysis and curation. Well, PDS had and still has hundreds of person-years of experience archiving planetary science data, curating it, serving it to the community, and supporting creators and users. There is no deeper well of knowledge to draw from in designing or redesigning a service-oriented archival planetary data standard. And as a quick example, I would note that Ray Arvidsson, longtime manager of the Geosciences node, was on CODMAC 1, and Ray Walker from the PPI node was in the planetary data workshop, as was Chuck Acton and Dick Simpson, and a large number of PDS people have many years under the belt. And finally, historically, PDS funding has stayed flat for years at a time. The PDS budget was never going to be robust enough to handle media migration, format migration, tool development, interface development, and all the processes necessary to support the ingest and curation of planetary data, let alone the new requirements for archiving placed on Rose's proposals. The only rational approach was to minimize the cost of maintaining the baseline archive. If you never have to do format migration, you never have to budget for it. If you know you're going to be supporting detailed search across the entire holdings, you design the metadata so that it is both possible and programmatically accessible to support that utility. PDS needed an integrated format and metadata system designed from the ground up for preservation, standardization, and automation. Most importantly, PDS needed a new archiving paradigm. Make the data fit the standards, which meant, practically speaking, we needed formats, first and foremost, designed to optimize preservation and the preservation task of archiving. That is, we needed archival formats. Because format migration is expensive and potentially dangerous, rescuing data from our own archives is expensive and potentially dangerous and embarrassing. The key to preservation is stability, and the key to stability is archival formats. What is an archival format? Oh, well, we also need an information model for all of our metadata to manage the complexity inherent in planetary science, but that's another talk. What is an archival data format? As those of us in PDS working on the new information model and system design debated this, and we debated it vigorously, we ultimately agreed that an archival data format has three critical attributes. First, it's software independent. That is, no specific implementation is required to read the bytes with certainty. Or put in a more tangible way, the format is so simple that no matter how information technology and programming evolve, a user could sit down and write a simple program from scratch to read the data and be successful. The data structure in the file should be hard to misread, and if the data are misread, either through programming error or metadata error, the problem can be easily diagnosed and fixed. This is possible because the formats are so simple, there are very few things that can go wrong, and they tend to produce characteristic errors. Second, storage formats for the bytes should align with the user's logical view of the data. In other words, if a user thinks of the data as consisting of an image cube with backplanes, then the image cube is stored as a 3D array in a contiguous stream of bytes, and each backplane is stored in its own separate 2D array of contiguous bytes. This makes it easier to read the separate parts, but it also helps to isolate errors in reading or metadata to a single part of the structure so that they don't impact other parts of the structure, unless your read error is that you got your byte offsets incorrect, and that's also pretty easy to diagnose. And finally, the data structure is described with exhaustive detail. Even things that we don't expect to change, like IEEE floating point numbers and 2's complement integers, or counting offsets and bytes, even those things are said explicitly in the label description. This is to counter unexpected changes in hardware and IT architecture. Adding new options for numerics or counting offsets cannot endanger existing data if the legacy units are clearly stated in the metadata for those data products. And in exchange for all of this, we get stability in the archive. Specifically, we get implementation agnostic, rigorous data modeling. The lack of dependence on implementation makes the entire system highly adaptable to technological evolution. We do not have to redesign the logic of the system in order to migrate it to new technology. And unless the base binary storage formats for characters and numbers change, format migration of the data should never be needed. Redirection of resources. PDS had been resource limited since at least 4 years prior to it becoming operational. Format migration is seriously expensive. When you alter bytes in data files, you run the very real risk of damaging the data. So any format migration must come with an additional external review of the result. Archival formats preclude this, which allows PDS to direct its resources to user services for both data preparers and end users, rather than spending it on maintaining the legacy archive. You get development efficiency. Because the data structures are source agnostic, it is possible to write code that is data source agnostic. You don't have to know who created the data to be able to read it. The data structures, via the exhaustive detail, contain all the information that is needed to perform low-level I/O without referencing the PDS schemas directly. The rigorous modeling results in well-defined, programmatically accessible structures that encourage third-party developers who can code to the model rather than to the specific data set. Interdisciplinary support. Simple, generic data structures do not favor one community of users over another and make specialized data more accessible to new users. As new analytical packages are developed, a single transformation routine can make all PDS4 archive data of a type available to that new environment at once with no impact on the preservation aspect of any of the data. Source agnostic metadata makes for source agnostic discoverability so that users can search for data based on the characteristics of the data, like wavelength range, in addition to the traditional source-based mission, spacecraft, instrument criteria available under PDS3. And finally, documents. Documents, ancillary data, and other supporting files that were locatable only by proximity in PDS3. In PDS4, they are fully described and accompanied by metadata that is comparably rich to that of the observational products themselves. And so, in summary, why PDS4? That's why. Other questions? Is anybody? Okay.
I'm here.
Okay.
So we have a couple of questions. Let me fix my echo.
Sounds very impressive.
Okay, my echo should be fixed now.
All right.
Michael I asks, why are the catalog files usually called index files now?
I did not know that they were.
Oh, okay.
I'm sorry, could this be a typo? Do you mean context files?
That may be the case, yes.
Okay. The catalog files in PDS3 were called catalog files because they were used to load a catalog. That's not true for context objects here. They are, in PDS4, the context objects are used to provide a hook, really, for a concept that is external to the data products themselves. But we have context objects for things like instruments and spacecraft and observatories and ground-based telescopes, the same way we had for catalog files because they're search criteria. But they are removed from the data collection dependency because the concepts are more general than the data. So when we have a spacecraft that's used for multiple missions, the context object gives us a hub where we can attach pointers that say, ah, yes, this spacecraft was also part of this extended mission. This spacecraft was formerly known as this and now is known as that. And you get the same thing with instruments. You can attach the documentation that describes the physics of an instrument and how you calibrate data from the instrument to the instrument context object as a pointer. So a user can look at a data product and say, that's interesting, I'm not familiar with that instrument, click on the link to get to the context object hub, and from that hub they can see, oh, here's a calibration document, here's a description of how the instrument was engineered, and here are 3 other data sets that were taken with this instrument when it was moved to a different telescope, that kind of thing. So they're a little more abstract is probably not the word I want, a little more separated from the instance of the data set to which they belong. And so we think of them as defining the larger context in which the data were acquired. And that's why they're called context objects. Similar, but slightly different function.
There's a question has a lead up, which is that the PDS seems very insular in making its technical decisions, partially because it's so experienced. Do you collaborate with outside institutions on those decisions and best practices?
Yes, we do. And part of the issue is that up until relatively recently, there weren't outside institutions. So because there weren't planetary archives, PDS was a leader in that respect. So the way the PDS was set up, the nodes are intended to be the advocates for the user community. So you've seen nodes manning exhibit booths at meetings, partially to stay in touch with a greater range of the user community than you meet if you just sit in an office and deal with the data. So yes, I go to meetings specifically to talk to users and get their input on how things are going and see what it is that's working for them and what isn't. We also have peer institutions now with the International Planetary Data Alliance and specifically with the PSA that we've been working with very closely as they grew out of the Rosetta mission, which has been going on for a long time, and other international agencies. So the PDS is a participant in the International Planetary Data Alliance. And we actually have one or two folks from the Planetary Science Archive who sit in on data design group discussions where we're working on tweaks to the system and looking toward version 2 of the PDS-4 standards. More of it needs to be done, and I'm not going to sit here and tell you that that's all we need to do, but we're working on it. And I hope that people will feel free to at least come and argue with me anytime you'd like to about what PDS is doing, because I really would like to hear what works and what doesn't work from what we've designed.
Michael is asking a follow-up question that he heard there will not be catalog files anymore for PDS-4. Is that true? And if so, how can we then get a local catalog to search the data offline?
I'm not quite sure I understand the context, but the catalog files did not contain indexing information. The catalog files only ever contain description. The descriptions aren't going away. The issue with the catalog descriptions from PDS-3 is that the descriptions got excessively long. They were supposed to be on the order of 500 or 1,000 words, and some of them have tables of contents. They are so exhaustive. The descriptions are going to be turned into documents that can then be formally referenced and tagged and have their metadata indexed. The catalog files themselves are part of what we use to connect the various parts of the archive, so I'm not quite sure how you would index them separately. I think I'm not understanding the question, really.
I think there might be a confusing terminology. Is that in the Open Planetary Slack? That's a great place to have that conversation.
Ah, yes.
And finally, this sounds like it could be a fun question. Can you describe the difference between formal and informal modeling?
Formal modeling, you start with a paper and a pencil, and you collect all the information, you categorize it, you normalize it, and you turn it into a schema. That's what was done to create the catalog collection for PDS-3. Informal modeling is, okay, so here are 3 data sets that we want to ingest, and here's what their data files look like. So all data is pretty much the same, right? Okay, well, let's just describe these. And then the next one comes in and it's got different line delimiters. Okay, so let's do something about that. And then the next one comes in and it has a vector in one of the table fields instead of just scalars. Oh, okay, well, we'll add something to cover that. So some thought was given to what is the effect on the data structure, how do we describe it, and how do we make sure that this doesn't have a negative backwards effect on a table that was already described. So you have to be specific about the things that you're adding and changing. But there was not an effort to sit down and say, okay, users are going to want to have to do things with images. How are we going to define images, and then how are the missions going to document things so that they're in our format? There was no systematic approach to deciding what you needed to record so that a user could read an image. or a table. Tables were better because frankly, you can't read anything if you don't have a fair amount of metadata in tables. So that's what I mean by informal modeling. There was some thought to what does this mean generally, but no systematic approach to describing all the attributes of an image that we wanted to record. What metadata are we going to use to describe them? What are we going to do when something comes in that doesn't quite fit this model? What parts are we going to require to be present? That sort of thing.